3-5, systems with 3 variables. So now in this section, we're going to go from looking at 2 lines intersecting to looking at the intersection of 3 planes, right? We're now going to go into 3-dimensional space. So our objective is to solve systems in 3 variables using elimination and to solve systems in 3 variables using substitution. Same techniques that we used for 2 variables, and that's what our essential understanding says. So to solve systems of 3 equations in 3 variables, we can use some of the same algebraic methods that we use to solve systems of 2 equations in 2 variables. And remember the difference. In 2 variables, we are finding the point where 2 lines intersect. In 3 variables, we are finding the point where 3 planes intersect. And we'll look at a picture of that in a minute. Let's do a quick warm-up problem. Okay? So, how much does each box weigh? Well, we have box A's, we have B's, and C's. Okay? Only one of them has a number. This is the only box that is labeled as, well, this one is the only box that's labeled with an actual number. But we have B and C. So let's write a couple of equations. So in my first little seesaw here, we can see that 2A is going to be equal to B. In my second one, I can see that C is going to be equal to 3A. So with a little substitution, instead of B, I can write 2A. And instead of C, I can write 3A. So that means that my 10 pounds is the same thing as 5A. So that means, divide by 5, that A is going to be equal to 2 pounds. So now because of that, I can rewrite these to be 2, 2, 2, 2, and 2. Which leads me to know that C is going to be equal to 6 pounds and B is going to be equal to 4. And that was a system of 3 variables, 3 equations, 3 variables. Won't always be that simple, but that's the general idea. Okay? So we can represent 3 relationships involving 3 unknowns with a system of equations. And we can represent systems of equations in 3 variables as graphs in 3 dimensions. The graph of an equation in this form, ax plus by plus cz is equal to d, where a, b, and c are not all 0. That is the standard form of a plane. We can show the solutions to this 3-variable system graphically as an intersection of planes. And here's the picture. Okay? You can see that in these 3 situations on the top, those planes do not ever intersect at one point. 2 planes intersect here, 2 there, and 2 there, but they never all come together in one. Same thing here. We have 2 lines of intersection because planes intersect in lines. So we have 2 lines of intersection, but they never all come together. In the third one over here on the right, all those 3 planes are parallel, so they never intersect at all. However, if we look at the situations at the bottom, these 2 situations actually have a solution. One solution for the left, and because all 3 planes intersect along the same line, that plane or that system has an infinite number of solutions. So just like before, we have 3 sets of situations. No solution, infinite solutions, or 1 solution. It's just in this case, there are 3 different ways that we can get no solution. But most of the time, when we're looking at these, we're going to get a graph, or we're going to get a picture that looks something like that. Okay? That my 3 planes, well, I don't have to draw the planes, I just need to know where they're going to intersect. Okay? So, let's try first with our 2 methods that we know how to use. Okay? We know how to use the elimination and substitution method, and we're going to use them to solve the systems of 3 variables by working with the equations in pairs. Okay? So we're going to, since we have 3 equations, we're going to pick 2 of them. Okay? We're going to pick another 2 of them, which means that we're going to use 1 equation twice. And when we get down to just 1 letter is equal to something, we're going to work backwards, and our solution, right? When one point represents the solution of a system of equations in 3 variables, we're going to write it as an ordered triple, x, y, and z. So we're going to graph it in 3-dimensional space. Okay? And if we can remember our 3-dimensional graph, coming out of the board is the x-axis, left and right is y, up and down is z. Okay? Hard to see in 2-dimensional space, but we'll do our best. Okay? All right, so the first one, let's solve a system using elimination. Okay, so we have our 3 variables over there. We have our three equations, our system in 3 variables. Something should jump out at you. Okay, equations are numbered, right, to produce the easy to follow. Okay, but look, something should jump out at you. The x's, all different coefficients. The y's, well, I have a 3, and then I have 2 are the same. So that would make for a slightly easier elimination. But if we look at the z's, we have a positive z, and we have 2 negative z's. So that makes for a very easy elimination. Okay, so to start, let's add 2 equations together. The objective is to get rid of one of the letters. All right, so if we are going to choose to get rid of z first, when we add 2 equations together, I must then get rid of z again. So if I'm going to add equation 1 and equation 2 together and cancel out the z, I then have to make a second set of equations. I have to add 2 more equations together to also get rid of the z. So it makes sense to add 1 and 2. So we're going to do 1 plus 2 first, equation 1 plus equation 2. And then we're going to do equation 1 plus equation 3, because that will cancel the z in each one, because in 1 z is positive, and in 2 z is negative, and in 3 z is negative. And like I said, it's okay to use equation number 1 twice. There's only 3 equations. You have to use one of them twice. Okay, so let's do this first, and then let's do that second. Okay, so let's take equation 1, which is 2x minus y plus z is equal to 4, and equation 2, x plus 3y minus z is equal to 11, and let's put them together. So that gives me 3x plus 2y, the z's cancel, which is what I want, is equal to 15. Okay? Now let's take equation. Now we're going to stop there, because I now have x and y. I can't take that any further until I have another equation with x and y. So let's take 1 and 3 and add them together. So that's 2x minus y plus z is equal to 4. And then equation 3 is 4x plus y minus z is equal to 14. Okay. So now, when I add these 2 equations together, we find that something really nice happens to make this problem a lot easier. 2 and 4 gives me 6x. The y's cancel, the z's cancel, and so it's going to be 6x is equal to 18. Well, x is now by itself, so I can easily solve this for x. So 6x, x is going to be equal to 3. Now that I know what x is equal to, okay, I can take x and substitute it back into any equation that just has one other variable besides x, which is this equation right here, which has x and y. So I can go 3 times 3 plus 2y is going to be equal to 15. So it's 9, 15. Subtract 9 from both sides. So 2y is going to be equal to 6. So, oops, divide by 2. So y is going to be equal to 3. Also, now that I have x, now that I have y, I can go back to the beginning and plug it into any equation that I want to solve for z. The only thing is, it's got to have x, y, and z, or it's got to have some other letter in z. Okay? And it's up to you, whichever one you want. Look for the one that looks the easiest. I'm gonna do with number 1 because I think that looks the easiest. So we have 2 times 3 minus 3 plus z is equal to 4. So that's 6 minus 3 plus z is equal to 4. So that's 3 plus z is equal to 4. Subtract 3 from both sides. Z is equal to 1. So there's my solution. So my solution, if I'm going to write this as a point in space, I'm going to have 3, 3, 1. X, comma, Y, comma, Z. Okay. On a graph, which is hard to do, okay, I'm going to do it in red. Remember that the x-axis is out here, y, and z is up and down. So I'm going to go 3 steps forward, 3 steps right, and then 1 step up. That would be my point. Okay? Tough to see in 3 dimensions. If you can do it, that's good. Okay? So generally a simpler problem because of what happened right here in these 2 equations right here. Having the x's and the y, or sorry, having the y's and the z's both cancel in 1 step left us with a very nice system to solve. Unfortunately, they're not always going to be that nice for us, okay? But we can do our best. So without solving these, looking at this equation, what variable would you eliminate first? My eyes jump right to the y's, okay? Because I have all the same coefficient and they're different signs. Down here, again, I jump to the x's because they're all different coefficients. And they're all the same coefficients, and one of them is a different sign. Also, another thing to notice is that these 2 are different signs, and there is no y in the first equation. So again, it might be easy to do the y also. Right? But try to stick to whatever equation is going to be the simplest for you to solve. Okay? Make your life easy. Okay? So let's look at an equivalent system, which is not very easy to solve. Okay? So unlike the first problem, where in our second step, 2 equations just 2 variables just cancel each other out. In this problem, nothing like that is going to happen. All right. So looking at this problem, you have to decide what to eliminate first. Okay. I can see that my x's have ones, a -1 and a 2. That's not horrible. My y's have 1s and a -2. That's not horrible either. The z's are the worst place to start because we have a 2, 3, and a 1. Okay? So if I was going to start this problem, I would start with trying to eliminate x. In order to do that, I need to make some sort of equivalent system. So I'm going to take equation number 1. I'm going to multiply it by 2 and add it to 3. Okay? So why do I do that? Never mind, I'm not going to do that. I'm going to take 2 times equation number 1, and I'm going to add it to 2 times equation number 3. So I'm going to have to multiply both by, I'm going to multiply the top equation by 2 and the bottom equation by 2. And that'll change the top equation into a +2, the bottom of equations into a -2. Which, I don't even have to do that. I can make this a little simpler, and I can save multiplying it till the second step. So let's save a multiplication by 2, because look, we have just an x and we have a -x. So let's get rid of x in the first 2 equations, and then let's multiply to get rid of x in my second equations. So let's just do x plus y plus 2z is equal to 3. -x minus 2y plus z is equal to 10. Right? Now, what happens? So we get x's to cancel, y's turn into -y, z's plus 3z is equal to 13. Okay. Good. So now we have y, we have an equation with y and z. Let me double check, make sure I did everything right. 3z minus y. Okay. So now we have an equation with y and z. Let me move it down a little bit. Okay. So we have an equation with y and z. So let's do the same thing. Let's take equation number 2 plus y plus 3z is equal to 7. And I'm going to take 2 times equation number 3. So when I multiply equation number 3 by 2, I get a -2x minus 4y plus 2z is equal to 20. Okay. Now when I add these two together, the x's cancel, okay, which is good. Negative 3y plus 5z is equal to 27. Okay. So now I have a system of two variables. I've gotten rid of x in both places. Okay, that's good. That's what I wanted. So here's my new system. Negative y plus 3z is equal to 13. Negative 3y plus 5z is equal to 27. Okay. So there's my system. Okay. Two variables, which we've dealt with before. Looking at this, I could use substitution because this y is by itself. So I could use substitution if I wanted to. I'm just going to take the entire first equation and multiply it by negative 3. That will get the y's to cancel each other out. So this equivalent equation is going to be 3y minus 9z is equal to 39, negative 39. Okay. And my old equation was negative 3 from the bottom plus 5z is equal to 27. Adding these two equations together, the y's cancel out, and we have negative 4z is equal to a negative 12. Divide by negative 4, and z is equal to a positive 3. Okay. Now we have z. Now we have to start working backwards. Okay. So I have 4 choices for z. I can put it there, 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 or there. Okay. I'm going to pick my original equation, okay, which would be this guy right inside the parentheses. Okay. So that tells me that negative y plus 3 times 3 for z is equal to 13. So negative y is equal, negative y plus 9 is equal to 13. Subtract 9 from both sides. So negative y is going to be equal to 4, which means positive y is going to be equal to negative 4. Okay. So now I have 2. Now I have y and z. Going back up to the beginning, I have to pick an equation which looks the simplest. I'm going to pick equation number 1 for x. So x, well, y is going to be minus 4 plus 2 times 3 is going to equal to 3. So that's x minus 4 plus 6 is equal to 3. So that's x plus 2 is equal to 3. So x is going to be equal to 1. Okay. So now I have my answer. Let's go down to the bottom. Let's write it. My answer is 1, negative 4, 3. And that is a 3-dimensional coordinate. Okay. So 1, negative 4, 3. If I wanted to graph this, graphing it in 3 dimensions, okay, in red, I'll do it in red again. That means 1 out, 4 this way, right, because it's negative, and then 3 up. So kind of a trick to see in 3 dimensions. Okay. But we went straight forward out of the board, then we went left, and then we went up in space. Okay. So let's now use a word problem, real world problem. Okay, we can set this up the same way as any other real world problem with a system of 3 variables. So you manage a clothing store and budget $6,000 to restock 200 shirts. You can buy t-shirts for $12, polo shirts for $24, rugby shirts for $36. And let's call that X, Y, and Z. Okay. If you want to have twice as many rugby shirts as polo shirts, how many of each type of shirt should you buy? Okay, so let's set up my system. So we know that first that we want 200 shirts. So x plus y plus z is going to be equal to 200. Okay. We then can budget 6 grand. So 12x plus 24y plus 36z is equal to 6,000. And my final equation says you want to have twice as many rugby shirts as polo shirts. Okay? So that means if I want to look at polo shirts, okay, I want twice as many rugby shirts as polo shirts. So if the number of polo shirts, I just need to take that and multiply by 2. So there's my equation. Now, this is set up as a perfect place for substitution because we have y is equal to something. We have z is equal to 2y. But the middle equation there is going to drive me crazy. So instead of that, let's come up with a new system. Let's come up with an equivalent system. X plus y plus z is going to equal 200. Okay? But I noticed that all of those variables in my second equation there are divisible by 12. So I can divide everything in the second equation by 12. So that would give me x plus 2y plus 3z is going to equal to 500. Okay? Because of that, it makes this system a lot easier to manage. And then, of course, we have that z is equal to 2y. Okay? So let's take that z and let's plug it in. Let's substitute into my system. So that would give me x plus y plus 2y instead of z is equal to 200. Okay? Which then would give me x plus 3y is equal to 200. Okay? Great. Let's stop there and let's substitute into the other equation. So that's x plus 2y plus 3 times 2y is equal to 500. So x plus 2y plus 6y is equal to 500. So x plus 8y is equal to 500. All right. So let's finish this off. All right. So now I have 2 variables and 2 equations. 200 and x plus 8y is equal to 500. Okay? I can solve this with substitution if I wanted to, or I could solve this with elimination. I'm going to use elimination. I'm going to take the entire first equation. I'm going to keep everything positive. I'm going to take the entire first equation and multiply it by -1. So that way, most of my answers will end up positive. So if I take this, multiply it by -1, I would get negative x minus 3y is equal to negative 200. Put it together with x plus 8y is equal to 500. And we get 5y is equal to 300. So that means dividing both sides by 5, that gives me that y is going to be equal to 60. Okay. Now that we have y, we can start going back and plugging in for x. Well, I know that x, I'm going to use the original top one, times 3 times 60 is going to be 200. So that's x plus 180 is going to be 200. So x is going to be equal to 20. Okay. And then going back to solve for z, I just need an equation now that has z in it. Well, that's the easiest equation right there with z, the one that I substituted in the beginning. So all I got to do is take y and multiply it by 2. So my answer for z is 120. So z is equal to 120. Okay. Now, you could write your answer as a point, 20, 60, 120. Okay. But it makes more sense to go back and say what your answers are. So way back to the beginning, that you would buy 20 t-shirts 60, right? 60 polo shirts and 120 rugby shirts. Okay? And that is solving systems of equations with three variables.